Okay, so here's a really classic dynamics problem, right? So this comes from Hibbeler, and I remember I was asked this question in the PhD qualifying exam, which you have to take within your first year of starting a PhD program, and this was an oral exam, and one of them is the dynamics. And so here's a problem that it's like fair game. So we have this small box of mass m. It's given a speed here. So they tell you the speed, and I don't know why they set it to square root of g times r, but they do. So it's not they don't have a numeric problem. And at the top of the smooth cylinder, so somebody's shoved it, right? And it's smooth. So we want to determine the angle at which the box leaves the cylinder, right? So there's a whole bunch of principles that we want to try to work through as part of this. I don't like how the things are showing through my paper, right? So maybe I could stick another piece of paper underneath here. I'll just flip these on upside down. Boom. Now it's not showing through, unless you have X-ray vision. All right, so I'm going to redraw this little thing, this little dome, little turtle shell thing going on, and let's draw this thing at an arbitrary angle. I think it's better to draw, which way am I going to draw the thing? I guess I'll draw it like this right here. There's a draw an arbitrary angle, and here it is, coming down, floating down right there. And so we're going to use work energy for this, and what we're going to find is the potential energy, right, is going to be dependent on here. Like so, right here is where R was. So this new location for a height right here, or this change, I should say, that's going to be like right there. If this is we'll call that a datum, and so we'll have with an M. So this height, that's going to be a change right here. We set that equal to R minus R times the cosine of theta right here. Because right here is like also R. So we're going to have like this is the R times the cosine of theta. So R minus R times the cosine of theta is going to be this height that would be at the original location. So we could say that KE1 is going to be 1/2 mass times velocity squared, which we were given right here, and it was the square root of it. So 1/2 mass, this thing squared is going to be 1/4 GR right here. All right, so what are we dealing with right here? 1/8 mgr is what they're saying. I don't know, for some reason. Potential energy 1 is going to be mgh, which is mg, let's say r times 1 minus cosine of theta right there, right? So you see that r minus r, that's why that's right there. U1 to 2, it's going to be conservation of energy, it's frictionless, great. KE2 is going to be 1/2 mv squared right there, right? And then PE2 is going to be equal to 0 because this is the datum, right? So at some point it's going to lose track. We don't know what that is, but it's going to happen right there. And there, by the way, that was theta. I should have put that as theta right in there, right? That's where I'm defining theta. Actually, they defined it for us. That's cool. All right, so we're going to set up this thing and say KE1 plus PE1. You know the drill. And so start plugging the things in. We have 1/8 times mgr plus mgr, 1 minus cosine of theta plus 0 equals 1/2 mv squared and plus 0. We got rid of a lot of m's. Yay, mass goes away. So we rewrite all this whole thing, and we find that v squared is equal to gr times 9/4. Why did I put v squared in there? I guess I just left it that way. That's why, because I felt like it. Minus 2 times the cosine of theta. Right there, right? So I had multiplied that 2 in there, and we get 9/4. I guess, yeah, we must have been trying for the, sure, okay. Yeah, I guess we had to add things together. Yeah, everything worked out. Sure, everything worked out. Yeah. Okay, and anyway, so, it seems kind of weird to me that we have that. Nah, I guess we're the lowest thing we could get into. All right, so now what we would do with it was like, oh, we have this we could get the velocity, we could make that the square root of all of that. So what we have to do now is use N to L, using Newton's second law, and take a look at this thing at an arbitrary angle. Right there, right? So we're going to have a weight of this thing, or mg, right here. And by the way, we're measuring our theta like that, right there, right? Taking a look back up there. That's how we're measuring our theta. So we might not get the same thing we always get. We're going to take his, we're going to draw the thing here, and here is Fn right in there. But where it's going to go away in a second. And we're going to have this as tangential and normal direction right here. And then we're going to have mass times acceleration in the normal direction right there, mass times acceleration in the tangential here. All right, so what we, let's see, how are we going to use this? Well, the central idea, determine the angle at which the box leaves the cylinder. What is special about that point? That goes away. Right there, right? So all that's left right here is, if we were doing this, let's just say it's in the normal direction, mass times acceleration in the normal direction, this is going to be positive right there. We would write that we'd have negative Fn, or not F capital N, because it's the normal, it's nothing to do with that N. And then, but then it's going to be plus mg times, and that's going to be the cosine. Did I get this right? The cosine of that angle right there, and then I'm going to have equal to m times the normal acceleration. It's the only thing going on in normal acceleration, but that's going to be 0 when this thing leaves. And so what we're going to have right here is going to have mg cosine of theta equals m, and then times our g r. Oh no, I'm sorry. Stop. We're jumping the gun. M-A-N. Boom. Get rid of our m's. Okay. So, but what is a-n? Remember that a-n is equal to v squared over rho, or r, onto the thing, right? So we already had v squared up here. That's why we never took the square root of the two things. So we could say, I'll take the m to cancel it out still. We have g r, and then 9/4 minus 2 cosine theta. So we could rewrite this thing out, and we're going to see that we have this 2 times cosine of theta is going to come all the way back over into here. Oh, we have a lovely, I'm going to be careful here. Wait a minute. Did I leave out an R? Where am I? Oh, yeah. This was over R. Dummy. So we had a G that goes away, a G that goes away, we have an R that goes away, and an R that goes away, and what we're left with is 3 times the cosine of theta equals 9/4. Whee! And so that's like theta is equal to the inverse cosine of 3/4. Theta is equal to 41.4 degrees. It's exciting. It is exciting, right? That you're able to get this angle. Is it? I don't know. Because we used this crazy velocity thing that has no physical meaning. I have no idea why we did it, but people ask this question all the time. It's a de rigueur, meaning that it's required. De rigueur, required. But now you've seen it. Loses all of its value? I don't think so.